Welcome to everybody. My name is Matteo Repetto, and I'm the technical coordinator of the GARD project. I'm working at CNR, the biggest Italian research institute, and as a research scientist. Today, we'll give you a brief presentation about the GARD project, which is about how to implement cybersecurity services for a cyber-physical system. With me, there is Giovanni Coppa, which is the leader of the use case that we will show today. Giovanni, can you introduce yourself, please?
Yes, thank you, Matteo. My name is Giovanni Coppa. I'm working for the WOBCOM. The WOBCOM is 100% total company of the city of Wolfsburg, and we are an internet service provider for the region of Wolfsburg. And today I give you an overview around the smart city ecosystem and IoT network in Wolfsburg and innovation from and the integration of GARD inside our ecosystem.
Thank you. So let's start with the presentation. So, as I already introduced, today we'll discuss how GARD provides an effective solution for building detection and analytics pipelines for digital service chains, and giving a concrete answer to cybersecurity issues brought by latest trends in the development of cyber-physical systems. During my presentation, I give a brief review of the evolution of cyber-physical systems in the last years, and I will point out the new cybersecurity issues that have emerged. I'll then explain the GARD concept to implement detection and analytics services in multi-domain digital service chains. So the starting point is the ongoing integration of software-intensive embedded systems, global communication networks, and cloud applications into cyber-physical systems. This leads to systems that are interconnected, collaborative, and provide users and businesses with a wide range of smart services. Cyber-physical systems leverage the Internet of Things and the Internet of Services to deliver systems that dynamically federate and interact with other systems and their physical surroundings. CPS will be able to sense and control physical world objects, even if such interactions have not been explicitly prescribed at the design time. As noted by Nessie in a white paper written some years ago, such dynamic actuation and the potential non-rollbackable modifications of physical world objects it implies will be a key differentiating aspect of CPS. This makes it more challenging to design, implement, test, and certify them in an efficient and effective way, not to mention cybersecurity aspects behind this revolution. The Internet of Things is not really a new paradigm. There are already well-consolidated examples of interconnection of smart devices. Remote control is today available for different applications, ranging from multimedia to device control. Protocols like UPnP and DLNA are used to discover devices in the surrounding and their capabilities, which is the preliminary operation before sending a command. Apps on smartphones and tablets have largely replaced the hardware remote controllers for TVs, drones, and other domestic appliances. This kind of applications is typically limited to home environments, and in any case to devices owned by the same person. Industrial and automotive applications have a broader scope because their discovery and communication protocols work over the internet rather than in local Wi-Fi networks. Machine-to-machine communication is today used to improve the automation of manufacturing and other industrial systems, to support predictive maintenance for vehicle fleets, to implement driver assistance systems, and so on. Also in this case, the scope is limited to specific devices owned by the same entity or a subset of its customers. The grand vision of cyber-physical systems goes, however, far beyond existing systems. Notably, it breaks the assumption of a closed world and looks at the dynamic composition of smart things, digital infrastructures, software technologies, and data. The perspective is to go behind rigid architectures designed to work statically in closed environments towards fluid systems that continuously morph at runtime according to evolving context. The combination of digital resources from multiple domains is often designed to create multi-domain data processing pipelines that transform raw data into value-added services. Novel digital products and services emerge in business ecosystem with a unprecedented rate with respect to the past, making monolithic ICT systems unsuitable to follow the market dynamics. The digital economy is therefore rewriting the rules of business and creating new models where services from multiple vendors are connected together to create, process, share, and also distribute data and content. Therefore, we like to see cyber-physical systems as large service chains, where the chain is defined by the ordered data flow through the different subsystems. The ICT industry is already tackling these new challenges. More agility in the creation and management of new services and products is being introduced through service-oriented architectures and everything as a service models that allow autonomic and dynamic composition of cyber-physical systems. But what does this mean in more practical terms? We can make two examples of concrete implications behind this evolution. So the first example concerns the Internet of Things. While in the past the interaction with the surrounding was a matter of connecting to specific devices, the focus has now moved to the data itself. In Europe, for example, the FireWare initiative has led to the definition of open and royalty-free APIs for getting the relevant context, independently of its physical source. If we need to know the temperature inside a room, we don't care the actual sensing device. We are just interested in the data itself. At this point, the data might be originated by a single or multiple devices, and such devices can change during operation without affecting the remote application. In the FireWare ecosystem, however, the availability of the data from a specific context broker must still be known to the application. But the International Data Spaces Association is now working on a more complete architecture, which includes the possibility to locate the data inside industrial data spaces. Even if the source does not matter to the data consumer for processing purposes, however, it may be important for security issues, including trust in the data itself. And this is one thing that is dealt by the GUARD project. The second example is represented by software orchestration, used for both cloud services and NFV services. The combination of dynamic provisioning and configuration management software allows to change the service at runtime, so to react to the evolving context, hence providing elasticity, redundancy, and resilience. Most important, such changes can be automated by defining suitable management policies in the service template. Eventually, this results in a construction that is evolving at runtime and makes the service topology partially unpredictable at design time. This new system notion is not easily captured by existing engineering principles, such as separation of concerns and divide and conquer. In other words, clear system boundaries will cease to exist and systems may be overlapping since a system is virtually defined and may be a transient notion defined temporarily for the purpose of executing a single function or business process. This is, for instance, quite common for Lambda functions and serverless cloud models. So despite of a groundbreaking evolution in virtualization and software management that we have just reviewed, cybersecurity paradigms have not evolved at the same pace. As a matter of fact, the security perimeter is still the prevailing model, but it cannot effectively tackle security aspects of cyber-physical systems, like integrity, trustworthiness, and data sovereignty in an effective way. In fact, common security paradigms for the enterprise are still based on the deployment of discrete security appliances that build a security perimeter that encloses all valuable ICT assets. The presence of portable devices already represents a problem, since such devices might get compromised outside the organization, but are typically considered trusted devices once brought inside. When enterprise processes include ICT resources from the outside, breaches must be created in the perimeter. VPNs and TLS are commonly used to extend the security perimeter till remote resources, but this may weaken the defense if such resources are not fully trusted. This is the typical case for IoT devices, which are often prone to tampering, but also for cloud services deployed in third parties' infrastructures. Security functions are offered by most cloud providers today, but they are difficult to be managed in a consistent way due to their heterogeneity. So, riding the virtualization wave, several vendors of security appliances are now delivering software instances of their applications, suitable to be embedded within their cloud applications, rather than in the underlying infrastructure. This helps build a uniform and integrated solution across multiple sites, but comes at the cost of additional resource consumption and overhead. For this reason, this approach cannot be typically adopted for the IoT and other resource-constrained devices. So the question is, what cybersecurity framework best fits cyber-physical systems? We posed this question some years ago, and the preliminary answer was that an evolution of existing paradigm is necessary in the direction of more autonomy, agility, and flexibility. The GAR project was indeed born to investigate the challenges posed by multi-domain cyber-physical systems and to propose new architectures and cybersecurity models that fit these environments. Differently from other parallel projects and initiatives, the focus of GARD is not on plain correlation, analysis, and detection aspects. Rather, we are more interested in understanding how to apply existing state-of-the-art detection and analytics capabilities to dynamic systems that evolve and morph at runtime. The main concept behind the GARD approach is rather straightforward. The same way management APIs are commonly used to orchestrate and combine digital assets into complex business chains, so a homogeneous set of APIs should be provided to orchestrate security capabilities as well. This implies that security functions must be embedded in digital resources, implementing monitoring, inspection agents, or detection functions. This is already partially implemented by cloud providers. As already said before, they often offer security functions like firewalling, antivirus, intrusion detection systems. However, common and homogeneous interfaces currently lack that are suitable to automatically compose such functions, so to create detection and analytics services for systems of systems. This often results in the need for cloud access security brokers to enforce consistent security policies across multiple clouds. The problem with cloud access security brokers is that they don't stop the proliferation of heterogeneous interfaces and capabilities, but only hide their presence to organizations. Of course, this means they must be continuously updated to follow the evolution of cloud services. While security in general entails a very broad scope, we focus on the implementation of detection and analytics processes only. The GAR platform mediates between security functions implemented in digital services and detection or analytics algorithms running in the platform itself. After considering existing standards like Oasis OpenC2 and HIETF interface to network security functions, we came to the conclusion that none of them fits dynamic and evolving systems. Therefore, we developed our own smart data model, which is able to capture the context in which each digital resource is running. This giving indication of the current hardware or virtualization platform, software vendor and version, as well as security capabilities available. Therefore, there are two main components in our framework, namely the GAR platform and security capabilities implemented by each digital resource. The GAR platform is somehow a sort of a dynamic security information and event management system that allows us to discover, configure, and pipeline security agents to a centralized set of detection and analytics engines. This largely removes the need for manual operation and the difficulty to reconfigure a CM for large, distributed, and ever-evolving cyber-physical systems. Security capabilities are exposed by the API mentioned before. It assumes the presence of security agents within each device, infrastructure, or application. In addition, a control agent must be present to describe the current execution environment, to link to chained resources, to perform configuration and management of the agents. Of course, it also provides token-based authentication and authorization mechanism to restrict access to internal resources to authorize the security providers only, which act on behalf of resource owners. The distinction between security and service providers is necessary to avoid conflicts in service management and security operations. The dashboard represents the user interface to the GARD platform. It allows to discover the current service topology and the monitoring and inspection capabilities exposed by each component. Security experts can therefore analyze this graph, identify vulnerabilities, and proper defense strategies. The dashboard allows to define security analytics pipelines by chaining monitoring capabilities implemented by digital objects with internal set of analysis and processing algorithms, including basic forms of reaction and reconfigurations. This could be especially useful in case the system changes over time. For instance, new components are added, removed, or deleted. The project is demonstrating the GAR platform in one use case in the smart mobility domain. It is a fleet management application that collects data from IoT devices installed on city buses, which will be described shortly. This is a typical example of a cyber-physical system encompassing multiple domains. As a matter of fact, there are several digital resources that are usually provided by different providers, namely IoT devices installed on buses. The application could also be extended with information coming from other appliances, like smart lampposts, parking meters, etc. A LoRaWAN network for the collection of data. A 5G or other kind of backbone connection, for example, a fiber network, to bear the data within the city. One or more cloud infrastructures for running the LoRa network server and fleet management application. And finally, the cloud application itself. This is a typical scenario where the service provider is not able to deploy its own monitoring agents, but must instead rely on capabilities provided by resources owners. And now I give the floor to Giovanni, who will discuss the use case in more details.
Thank you, Matteo, for the introduction of GARD project. Now, I will give you an overview of the use case and integration inside the smart city ecosystem of Wolfsburg. We know that the IoT world evolves very fast, leaving some of the currently employed technology behind. We need high availability and performance, low energy consumption, and high privacy standards. The purpose of this project is to provide a cybersecurity framework for complex business chain, composed by public services and exchange data and commands through the open API. GAR targets concrete technologies and architectures, for example, fiber and the international data space connectors or architectures. Originally designed to be played on scooter, we changed the paradigms for our public transportation company in Wolfsburg. With this target, we developed an IoT sensor for with an interface for and integration with the bus computer board. It was really hard work, and we invested a lot of time for this integration. All these interconnected mobile devices consequently generate big volumes data. Thanks to good smart city ecosystems, IoT network in Wolfsburg, and the strong innovation, we introduced the first guard sensor in the bus very soon. Guard integrates complementary technology like monitoring, detection, and visualization in an open and modular architecture, and together building an interoperable framework. On the top of the software is now the collect big volumes of data from vehicles. In addition to this, an exponential increase in real-time based application fuel even more user demands. Edge and fog computing paved the way to a new different approach in like the lake, not only the cloud for computational and storage resources. In the picture, you can see some screenshot of our gateway installed around the city with some simulation. As well, we use a public radio and a network quality test. Please take attention. We use a multiple providers, vendor and partner, and some information about our backend software like monitoring and alerting manager. All of this is an integral part of Wolfsburg Smart City today and IoT ecosystem, and made available for the GARD project. Well, just a few months after the creation of the sensors we installed in the buses, we have optimized the solution by introducing a new scheduling, collecting the data, and backend ecosystem. This was the project, the first phase of real-time and live data collect. Together with partners, we addresses the proliferation of real-time application by shaping a deadline-focused algorithm, and we analyzed the result to evaluate the system behavior under various constraints. The device installed in the vehicles of the public transport services, fleet collect location data, bus occupancy level, etc., which are sent in real time to the develop software services that ingest, clean, and clearly present to the status of each vehicle to the end users, providing details information on the status of the public transportation services. The whole system will be composed of many software elements deployed in heterogeneous execution environments like car, cloud, enterprise, and operated by different players like car owners, navigation services, road operation, and other drivers, as we can observe in the next slide. With this increasing integration of cloud, edge, and fog resources in the critical business and industrial process, a clear separation of internal and external resources is no longer possible. Modern digital services are generally composed along the three dimensions of infrastructure: legacy, enterprise, etc., cloud, fog, edge, computing, IoT, and some software technologies and data as well. The definition of services basically consists in the interconnection of software modules deployed over heterogeneous infrastructures and domains, and accessing local and remote data. The application developer by GIG and WOBCOM, in this case, has been implemented in Wolfsburg bus fleet. The services required for the application have been deployed in WOBCOM infrastructure with a microservices-oriented structure. This allows us to deploy in a controlled way all of the services necessary for the processing and presentation of data in a controlled way. The application can be defined into a layer of IoT stack. The data collecting layer, sensor inside the bus, sensor distributed around the city. The network layer, long-range area network, LoRaWAN, Wi-Fi LTE connectivity, fiber optics, cloud connectivity, messaging buses. The information layer, application presented to the final consumer of the services, context enriched the M2M interfaces. You can see some screenshot of our dashboard on the slide. The smart city scenario is based on real use cases. As part of digital strategy, the city of Wolfsburg is developing and the deployment an ICT infrastructure for building smart services to help issues like waste management, parking, metering, pollution, and transportation. Just a few months after the creation of the first sensors, we are installed in the buses. This is another step in our continuous innovation and progress of the project GUARD. First of all, we have developed a new version of the GUARD sensor, you can see here. An important time to analyze new scenarios, risks, and opportunities. Now the infrastructure is based on modern sensors network covering the city and its surroundings, including several smart gateways interconnected by a high-speed, low latency fiber network through the whole city. The next slide, you can see the implementation of GUARD agents. As I say, WOBCOM already provides the free internet access by Wi-Fi, like free Wolfsburg in the city. The plan is to provide a similar services to many IoT devices through LoRaWAN network, so to create connectivity among things and citizens. As a public application, it's exposed to attack that can compromise the availability of the services as well the data handled by the application. The use of GUARD platform agents provide a large of security and different level of ensure availability, robustness, trust, and confidence. The cloud application will be hosted on Wolfsburg city infrastructure. The internet bridge connects the EBS bus of the buses to collect position information, operating data, and onboard sensor and command and query from the integrated or portable users interfaces. The data will be collected and processed by the system using firewall services. Both the edge installation and the central data can hosted application of third party that creates smart city services. Now we can see the guard agent inside our ecosystem in the city of Wolfsburg. The graphic below showed the ecosystem behind the worked and illustrated the evolution framework approach the mapping between the guard components and the infrastructure activities. For example, we have the chirp stack forwarded is a guard agent that can be configured and collect and forwarded LoRaWAN related messages coming from an MQTT broker to the Kafka broker. It can forward it to network messages that is the communication between gateway and the network server and application server related messages. For example, they code uplink messages. Both type of messages streams are consumed by other guard agents, for example, iMiner and net anomaly detector. The iMiner, the next agent, is deployed as a Docker container within our testbed infrastructure, an associated container that runs the LCP client, allows the control and configure the iMiner via the central guard platform. The iMiner receives input from the LoRaWAN gateways via MQTT message queue, as well as along from the chipstack application server. iMiner, like all of our agents, are open source. The last of our agents is the elastic bits. Elastic bits are a set of lightweight data shippers developed in the framework of the Elastic Stack. Their scope included monitoring and inspection of system operation and network traffic. A really important component in our integration are the EDS connector and the context broker. The application also included other security agents, as a vulnerability scanner that analyzes host and open ports on the network, the IDS connector, and two packet inspection tools, VDPI, Virtual Deep Package Inspector, and the PGA filter, the packet generating algorithms. The following slide shows the guard platform components involved in the test execution. The first case presented the integration of PGA filter agents in guard framework for identify anomalies and attack LoRaWAN and how we protect LoRaWAN network detection result by PGA filter are published to Kafka bus to made available for guard security services and guard dashboard. In the figure above, number one, we illustrate the chipstack exploit. The gateway B was hijacked by an attacker. It reads to the topics for uplink events and replay an uplink frame from gateway A. The chipstack network server received both message and due to the invalid frequency field drops both messages. They are giving uncertainty whether the attack is successful or not. A message may be dropped. 3.4, the exploit sent the manipulated packet multiple times in a row to increase the likelihood of a successful attack. The high minor agent passes the message from the LoRaWAN gateway provided via MQTT. Moreover, science the attack sends in the same message multiple times in a row. To attack could also be detected as an increased event occurrence in a short period of time. All of these scenarios show what an important rules guard inside an IoT smart city ecosystem like the city of Wolfsburg. The most tangible benefit will be improved services level agreement, SLA, also included strong security feature that can be defined by each actor. Yes, thank you. Thank you for attention.
So if you want, you can contact us at the following contact points, me as the technical coordinator, Armen Dusa as the overall project coordinator, Giovanni Coppa as the use case leader, and also Angeles Tegado as a dissemination manager of the project. And you find also listed here our main social media and website. Thank you for your attention.
Thank you for your time.